I get 2 Christmases.
Yeah.
I get 2
Well,
this.
yeah,
I'm like, Jojo, no, this isn't good.
yeah. No.
Oh, it's
not. All right, so let's take a look at this. These numbers are real. These are good numbers to toss around. So Colstrip is actually at 2.2 gigawatts. These are Mark Olson's numbers, and they are accurate enough. So what he says can produce over 200 megawatts of electricity capacity, which is true, and it's 2.2. There are four separate generators there. A pair of them are at 300 meg and change, and the other pair at 600 and change. So 200 megawatts of electricity burning sub-bituminous coal to produce it. Assume that we're running at 50% capacity for one day.
1,000 megawatts.
So capacity equals 2,000.
We're doing number 4?
Number 4, I think so, yeah. Number 4? Yeah, number 4. So capacity equals 2,000 megawatts. And for the day, we're going to run at 50% capacity. So the run equals 1,000 megawatts. All right. How much electricity as megawatts are produced in one day? Megawatt hours. Now, this is critical. I'm not, and this gets right back to day one. What's the difference between power and energy? So we, yeah. So let's just look at this in 2 separate ways. So if this were energy and this were time, we'll just say this is one day. Basically, what we're looking at, this is the capacity. The slope of this line is 200 megawatts, which equals, or sorry, 2,000 megajoules per second. Right, that's the way to think about it. But we're only, and that would be this much energy. But we're only running at half of that. So this other slope right here is your 1,000 megawatt slope, but we're only going to produce this much energy. So again, think of power as the slope of that line, and think of energy as the area under the curve. That's the way to think about these guys. Okay, so energy equals power times time, all day, forever, and ever. How much electricity? Megawatt hour. So this is fairly straightforward. Not that big of a mind bender. So 1,000 megawatts times 24 hours equals 24. Carry the 3 zeros. Megawatt hours. Pretty easy. Okay. Also, how much coal is burned in tons that day? Use the heating value found in figure 5.6 of 24 gigajoules per ton, and assume we're running at 30% efficiency. Okay, here's where it gets a little bit tricky. So 24 gigajoules per ton, 30% efficiency. So let's write that down. 24 per ton, 30%. I'll use capital T for ton. I'll write this down as just energy, sub D for energy density. Use whatever you like. And then the efficiency So that's an eta equals 0.3. So this is how much electricity is coming out. That's what the problem says. It's coming out at a rate of 1,000 megawatts. So at what rate is energy going in? So that's electrical energy coming out. At what rate is chemical energy going in? How do we do that? I guess the first question to ask, is it coming in faster or slower than it's going out? It's coming in faster. Yeah.
You gotta put the brakes on it.
So I'll actually let you chew on this for a little bit. I'm gonna pause it and let you play with this a little bit. So here we are. I think we've got a solution here for problem 4. Let's just take a look at it. I just started with the efficiency, and there's two ways to look at it. Efficiency, either as the energy out divided by the energy in. We know that the energy out is going to be less, because nothing is 100% efficient. Or we could look at it on a power basis. So we're either comparing these two triangles to each other, and or we're comparing the slopes. And you can see they're the same thing. They lead to the same conclusion. So since we were given the power, well, I just chose to do it in terms of power. You could also do it in terms of energy. So I said that the coal is flowing into the plant at a rate of 3,333 megawatts. And you're like, oh shoot, that seems kind of weird. How do I measure coal in megawatts? Don't I measure it in tons? Well, you do. So now we just run it through the unit analysis. So 3,333 megawatts is the same as 3.333 gigawatts, which is the same as 3.33, et cetera, gigajoules per second. So this is how quickly energy is flowing in. We know that coal has an energy density of 24 gigajoules per ton. We know that the answer we're looking for is tons per day, so tons has to go in the numerator. Therefore, gigajoules is in the denominator. So really, if remember back, like each one of these, we're really just multiplying by 1, because there's 24 gigajoules of energy in a ton of coal. And again, we're multiplying by 1 because there are 3,600 seconds in a day. We're multiplying by 1 because there are 24 hours in a day. And we come up with 11,988
Nice. I got really close.
tons per day.
I got 12,000 tons of coal. But I did it the opposite way, off of energy. I took the efficiency of the 24 gigajoules of coal energy produced from a ton of coal, and it reduced my output to 7.2. From there, I converted that to kilowatt hours, and then
Okay.
further converted it to 2 megawatt hours per ton.
Okay.
And then divided that by our total 24,000 megawatts.
Nice.
Megawatt hours.
Nice. Okay, thanks. And then, so there's 102 coal cars disappear into Colstrip on that day. And if you remember back, I just did a little searching here. I think we did this problem before. If you remember back, we actually ran the global coal consumption. And
A while ago.
yeah, so we did that 16 terawatts, 30% coal, and we came up with, it's either one coal train running headlong into a single global power plant at 180 miles an hour, or 3 trains all running 60, and that's how fast we burn coal on planet Earth. It's kind of wild. But the numbers, if you do it for Colstrip, running at full capacity, a car disappears into Colstrip every 5 minutes. Okay. On the one hand, it seems really big. On the other hand, it seems really small, because the world's a big place, right? It's kind of in your perspective. All right, let's look at problem.
You're gonna get a lot more claustrophobic the less oxygen there is in the atmosphere, though.
Yeah. Nikki Fear rode her mountain bike up to the Mount Loa, Hawaii station, where they actually measure global oxygen. Yeah,
She just got an award too.
she did. And I had a chance to talk to one of her co-awardees, Susan Petty. They're, doing some of the engineering for converting Colstrip to geothermal.
Okay.
Expensive.
But necessary.
Yeah.
Yeah, Nikki's busy.
Yeah.
She's when we're going to Vietnam, she's stopping off in Japan for a week to ski over there.
Yeah. Guys, let's knock this thing out. How much CO2 into the atmosphere in tons? Assume that the plant has no recovery, 55% is carbon. All right, so here's the way to do it. I'll just give you a little, I don't want to call it a teaser, but I'll give you a hint.
Which
So-
one is this for?
This is the last problem.
5, okay.
So CO2, so basically what we're looking at is carbon plus oxygen yields CO2. I'll let you do the numbers, I'll just kind of show you the way. Carbon has a molecular weight of 12. Oxygen has a molecular weight of 16. So CO2 has a molecular weight of 44.
Isn't there 2 different oxygens then? Oxygen 16 and 18?
I think there's even more than that. I mean, there's as many as you like, but it kind of, we're just going to keep it to
Just
2 significant
right now.
digits. Yeah. So the point is, for every 1 ton of carbon that goes in, let's do it this way. Let me just think about that for 1 quick second. We're good. Okay, so here's the way to think about that. So here's the stoichiometry. 1 carbon atom plus 1 diatomic oxygen becomes 1 CO2 molecule. Carbon has a molecular mass of 12. Oxygen has a molecular mass of 16. CO2 has an atomic weight of 44. So 1 ton of carbon in releases 3.6 tons of CO2. Now, in a picture, here's your oxygen atom with 32 atomic weight. Here's your carbon with 12. So for every 1 that goes in, 3.6 come out. For every 12 that go in, 44 come out. That's the way to think about it. And then use that 55% number in the problem set to reduce it, because other stuff besides CO2 comes out. Yeah, there you go. And then you just multiply it by how many tons, and then the answer drops right out. So, all right, thanks. And I'll be here Tuesday. Won't hurt my feelings if you're already off on turkey break, but I'll be here. So, thanks, guys.
Thank you.
Thanks. Yeah.